So how we define what's a median space? A median space is a metric space with the following axiom: that for any 3 points there exists a unique point which lies in the intersection of the three intervals. And here the interval between A and B is the set of points that lies between A and B, in the sense that the distance between A and B is equal to the distance between AX plus the distance between X and B. And here we don't assume that the space is geodesic or even connected. But if you assume the space to be complete and connected, then one can show that it is a geodesic space, and one can define the interval AB to be the union of all the geodesics connecting A and B. And in general, in these cases, when the space is geodesic, the space is far from being uniquely geodesic. Between A and B, we'll have infinitely many geodesic connecting A and B. And the only case where the geodesic coincides with the interval is the case of real 3. So these are metric space, such that for any 2 points there exists a unique curve which connect them without backtracking, and such a curve is the support of the geodesic. And here we should consider any 3 point. The 3 geodesic will intercept in a unique point. Other examples are given by cat-zero cube complexes. And yeah, these are complex of cubes. As I said, these are complex of cubes that are glued together isometrically along their faces, where each cell is endowed with the cat-zero with the L2 metric. And when we consider its length metric associated to the cat-zero cube complex, we require it to be negatively curved. We require it to be cat-zero space. But now, if we see the cat-zero cube complex with its cat-zero metric, it is uniquely geodesic, and it is not real 3, so it's not a median space. But if we restrict to its zero skeleton, and we endow it with the combinatoric metric, we see it as a graph, then it would be a median space. And in fact, it is a if and only if. The zero skeleton with the combinatoric metric being a median space is equivalent to say that the whole cat-zero cube complex is the whole cube complex is cat-zero. Other examples are given by L1 when we consider the product of the L1 product of a median space is also a median space. For instance, if we take R2 with the L1 metric, the interval between 2 points is a rectangle having extremity these 2 points. And here we have incountably many geodesic. We have this geodesic, this one, this one, this one, so on and so forth. Instead of considering a finite product, we consider an infinite product indexed by a measured space, in the sense that we consider L1 integrable function over a measured space. Other examples are given by asymptotic cones over space that verify coarsely the median axioms. So, for instance, the hyperbolic Gromov hyperbolic space can be seen as a coarse version of real trees, and when we consider asymptotic geometry when we go to the asymptotic cone. When we see the space from far away, what we will see is a real 3, and it will be far from being locally compact. For instance, if you consider a hyperbolic group, finitely generated hyperbolic group, its asymptotic cone will be homogeneous, and at each it will be a real 3, homogeneous real 3, and each point is a branching point having incountably many branches. And also, for instance, it was shown by Bowditch that the Teichmüller space, either with the Weil-Peterson metric or Teichmüller metric, that it is a coarse median space, and the same for the mapping class group, and their asymptotic cone is a median space, which is of say higher dimension. It's not a real 3. There's also finite dimension. Well, here this example will not be relevant in this lecture, but yeah, we have also a canonical median space associated to Hn, in which Hn embed isometrically, and the embedding is equivariant by the action of the isometric group of Hn. And also the embedding is at a finite Hausdorff distance inside the median space. And this example is interesting because, well, it is of an infinite range. Here, the range is the equivalent of the dimension in this setting, because we don't consider the topological dimension as the space can be discrete. What we characterize dimension by the dimension, the highest dimension of a cube that we can embed isometrically inside the space. It's zero skeleton. So this median space will be of an infinite range, but it is locally compact. Instead of these L1 space are not really interesting because they are too big, and any median space can embed isometrically inside such a L1 space. And here too big in the sense that we can't really do geometry with them, because in median space a main tool is a Hall space, which is a convex subset with convex complements. And in the case of, in general, for when the median space is of finite range, these Hall space are nicely embedded inside the space. They are either open or closed, and they are bounded by a convex subset, like a hyperplane, which is a median space of lesser rank. But in the case of the L1 space, if X mu is not does not have a atomic measure, then any Hall space is dense in the space. So they're not really does not have a nice topological separation in the space. Okay, so not only Hall space exists, but for any 2 points, there exists a Hall space which separates them. This theorem is ensured just by the axiom of median space. And this space of Hall space has a natural structure of measured space, and it verifies Crofton-like formula, where the distance between, or say the structure of a measured space, the sigma algebra is generated by these subset of Hall space, which are the subset of Hall space that separate X and Y. And the measure on such subset of Hall space is equal to the distance between X and Y. Now we have a natural compactification of the space called the Euler compactification. We can define it through Hall space, where elements of the boundary are characterized by the subset of Hall space that points toward that direction. Or we can define it by considering the embedding of X inside the product of interval, endowed with the product topology. And in the finite rank case, the intervals are compact. So the compactification of X is defined to be the closure of X inside this embedding. It is this map is injective. This is embedding by the separation theorem. And here the map is defined through the projection. You take any point X, you project it into the interval AB. And the projection coincides with the ternary operation. Projection onto the interval AB is exactly the median point between A, B, and X. We denote it by X bar. And we have a canonical decomposition of X bar as X disjoint union the boundary. Now, if the space X is locally compact and also connected, we need connectedness, then X will be open inside its compactification. But in general, if we assume that the space is not locally compact, or also if we assume that it is not connected, but this is a superficial condition, then X is in general is just dense inside the X bar. It is not necessarily open. And with regard to the boundary, it is not necessarily closed. Yeah, for the same reason that we just said. So now, if we consider the topology induced from the compactification on the Euler compactification on X, and with regard to the topology induced on X, it is the same as the topology generated by open Hall space. And also it induced the same Borel structure as the one given from the metric on X. So this remark is to apply a metric ergodicism. Now, again, inside the Euler boundary, we have two parts. We have the regular part, which sometimes corresponds to the tree-like direction toward the infinity, or can also see it as the limit point of hyperbolic element which are contracting, which contract the space. And in the setting of a median space, it can be characterized by a subset of a Hall space. So it is a function of infinity, and it is characterized by a subset of yeah. Let's consider an example for that. Just consider, for example, the universal cover of a torus, and glued with a circle, a ring, and consider the universal cover. And here the torus, we undo it with the L1 metric. In the roller boundary, so we will have flat part in the space, and we have also direction which correspond to direction following the tree corresponding to this space. So if we consider the roller boundary, we will have in the flat part, we will have this following point. By the way, it is stratified by components, where each component is a median space of lesser rank. And you have also other points which correspond to following the other direction, following the tree-like direction. We have also points. And how we characterize such point? We characterize them by the sequence of a Hall space. Which points toward that direction, so that the intersection of such Hall space on the regular compactification is equal to the regular point. And for each this family of Hall space are pairwise strongly separated. That is, they don't have a subset, a Hall space which is transverse to both. For instance, if we live inside the flat part, consider any two Hall space which cut the half part, they are not strongly separated. They have a Hall space which is transverse to both of them. And in fact, when you take two Hall space which are strongly separated, you can define many hyperbolic elements. So let's say we have two Hall space that are strongly separated. They don't have a Hall space which is transverse to both. You can define many contracting elements, or can define this way, or say it this way. If you have a hyperbolic element which acts is transverse to two strongly separated Hall space, then this element is contracting. It looks like the hyperbolic element of a hyperbolic space. That is, when you consider the inverse image of a finite segment, it can contain balls of arbitrarily large radius. And here, the existence of such a boundary is ensured as long as we assume that we assume mild condition on the isometry group. If we assume that the isometry group does not have a finite orbit, or, well, first we need the assumption that the space is irreducible. This is not a mild assumption, because you take any median space of finite rank, it's split as a product of finite irreducible median space, and the isometry group up to a finite index is given by the product of the isometry group of each component, each factor. And yeah, here, as long as we assume that the space is irreducible and that isometry, the action of isometric group does not have finite orbit and does not, and also is minimal in the sense that it does not have a closed convex invariant subset, then the regular boundary is not empty. The contracting element is insured. So now we begin by giving the big lines of the proof of the superrigidity of homomorphism. So the first step of the superrigidity of homomorphism, so we have a group. Okay, so maybe here for now, we assume that the group is just finitely generated, say finitely generated. But we can see later that we can assume also that it is a locally compact second countable group. But for the first second, let's assume that it is just finitely generated, it is countable, and assume that B is a strong G boundary. That is, it is a measured space with the action of G on B, which is minimal and doubly embodied. Here, moreover, we assume that the action of G on B times V is metrically ergodic. And in general, the first step of the superrigidity result is the construction of the boundary map, which goes from B to the boundary of the space X. And in our setting, so we feel X is a complete separable irreducible median space of finite rank. Now, if we assume that the group is finitely generated, we can discard the assumption of the space being separable. Then there exists a unique G equivariant map from B to the roller boundary X. And moreover, this map lies essentially in the regular boundary X. And also, it has a strong uniqueness property in the sense that you take any measurable G equivalent map from the product of B times V into the roller boundary, then it depends only on one of the variable, and it is mapped by the boundary map V. And for the proof of this theorem, as elsewhere, the first step is by amenability. We have a map which goes from measurable G equivalent map, which goes from B into the space of probability measure on X bar, and we want from this map to descend into a map which lies inside delta X. Note that if the space is locally compact, the space X is locally compact, then its boundary will be also closed, and it will also be compact. So we can consider directly delta X. But in the non-proper case, it is not ensured that delta X is compact. So we have, by amenability, we have G equivalent map from B into the space of probability measure on X bar. And in the case of Margulis and Zimmer superrigidity result, how they obtained a map from B into H times L, they first show that, well, we don't really care about the ambient space, as long as you are assured that the image lies inside one orbit, and the stabilizer of a point is nice. In their setting, I show that the stabilizer of a point is also an algebraic group. And they show that also the action is smooth. That is, orbits are separated by countable subset family of measurable subset. Hence, by the ergodicity of the action of G on B, the image lies necessarily in one orbit. So, but we don't have it in the general setting. We don't know if the action is smooth. We don't know if there exists a countable subset of measurable subset that separates orbit. And also the stabilizer of a point on the space of a measure. We don't also know how it is inside the group. Instead of that, what we consider the a barycenter map. We try to associate to each probability measure a barycenter. And here, how we define the barycenter, we define it through Hall space. Is you take, say, we have a space. And we have a probability measure on this space. And how we characterize the barycenter, we characterize it by a Hall space. We fix a Hall space, and the Hall space will cut this space into two parts. And the barycenter will lies in the part having measure bigger than 1/2. And if we consider this Hall space, this part will have measure greater than 1/2, and so on and so forth. And then we consider the intersection of all such Hall space having measure bigger than 1/2. So we define the barycenter being the intersection of all such Hall space, which are closed. We are saying that they are closed, and they have a measure bigger than 1/2. And so this gives us closed convex subset inside X bar. In general, it's not a point when the measure have a non-negligible subset of Hall space having measure 1/2, then this intersection will not be a singleton. It will be a space. For instance, if we have a such measure which have a disjoint support, then all these Hall space are have a measure 1/2, and so we'll have all this convex subset which lies in the barycenter. But using the ergodicity, the double ergodicity of the G action on B, we can show that regarding the boundary map, for almost all element in B, the image is the barycenter of the image is a singleton. So this defines a map into X bar, and also we can show that this map is measurable. So now the second step is to show that this map lies inside the regular boundary. And for that, we also use the double ergodicity. We show that if you take any two element in B, and you consider their image, you can show that their image is separated by arbitrarily big number of strongly separated hull space. And again, by double ergodicity, you show that this subset is of total measure. So. And this regular boundary verified the following property. If you take any three distinct points in the regular boundary, their median point lies in the space X, inside X. And this combined with the metric ergodicity shows that any measurable G invariant map from B times B into the boundary is of the form phi times the projection into one factor. Yeah. And how we do it? If we consider such a map, we consider the following construction, which is borrowed from paper of Bader, Furman, Capras, Sisto, which he did in the case of hyperbolic space. But in the case of hyperbolic space, you don't really have a median point, but you have you associate to a triple of point and the boundary, you associate to it a bounded subset. But here, what we consider the following map. And if C is distinct from phi B2 or phi B1, then necessarily this map lies in X. And this is ruled out by the metric ergodicity. So almost everywhere we have FC either coincide with phi B2 or phi B1. So now, remark here, we didn't assume anything about the group G being of a higher rank or anything. So this work as long as the action, we assume that the action on X is Euler non-elementary and Euler minimum. Yeah, now we'll go a little bit quicker because they are taking a lot of time. So now in the setting of, let's say, irreducible lattices inside a product of G1 times G2, the strong G boundary is given by a product of the strong G boundary of G1 and the strong boundary of G2. And again here, we have the following theorem, which says that the boundary map factor to one of the factor either to B1 or B2. And also here the proof is borrowed from the Bader-Furman's approach. So now we have that the boundary map factors to either B1 or B2. So let's assume that it factors to B1. And what we consider on the median space, we consider the median space obtained as the median subspace obtained as the median closure of this regular boundary. So for any 3 points, you consider the median point, and you iterate the operation until you obtain a median subspace. And this subspace is invariant under the action of the whole isometry group of X. And the action of, we have a representation of gamma inside isometry of Y. And through this boundary map, we know that the group G1 will act on B1. So in particular, it will act on its image, which lies in the regular boundary, which can show that it is the whole, almost the whole regular boundary. And how we extend the action of gamma into G1. So as the gamma is irreducible, its projection inside G1 is dense. And for the action for the representation to extend into G1, one needs to show that if you have a sequence which converge to identity inside the G1, then it will converge to the identity inside the isometric group of Y. And for that, we used the action of G1 on the image of the boundary map inside the regular boundary. Yeah. Yeah. So here uh, the action on the Y extend to G, and it is through only one factor. In our case, the G1 factor. Now, also quickly with regard to the cocycle superrigidity of cocycle, the first step is the same, and first step is to construct, let's say, a boundary map, which is a alpha equivariant section, and we show also that it is in the regular boundary, and it is unique in a strong sense. So this part, the argument looks like the superrigidity to the construction of the boundary map for the homomorphism of G, but the argument is adapted to the language of Cocycle, and use the fact that if as the action of G on omega mu is preserved measure and is ergodic, so the G action on omega times B is also metrically ergodic. And also the action of G on omega times B is amenable. And yeah, so for this part, we construct a G invariant map. And to deduce the superrigidity of homomorphism, this boundary map, what will give us? So we have a boundary map which goes from omega, and we show that it depends only on one factor times B1 into the regular boundary. So when you fix second variable, what you obtain? You obtain a gamma invariant section. Here the fiber are X, and the basis is omega. What you will obtain? You will obtain alpha G2 invariant subset, invariant section. So the action of G2 on such a section is trivial. It's stabilized such a section. And this section, if we consider, for example, 3 such invariant section, and we consider their median point, what we will obtain? We will obtain an alpha G2 invariant section where the fiber is omega, is Y, and the basis is omega. So we will construct infinitely many alpha G2 invariant section. And so this space of a section is not really endowed with, it is a G1 invariant space. And for each element, for each of this section, the action of G2 is trivial. It stabilizes each point of this section. So And now what we can do with that space of section, but we can show that this one is, we can undo it with the metric, and it is isometric to Y. So now we have defined an action of G on our median subspace. Also here, it can be more convenable to assume that Y is a countable subset. In fact, we can, if the action of the isometric group is roller non-elementary and roller minimal, and the space is irreducible, we can show that there exists a dense, or not a dense, a countable invariant subset, median subspace in the space. And so here we can assume that this space of section is also countable. So we can naturally undo it with the median metric. So if you take any two such a section, you integrate along the distance, and what you obtain a median space. And the claim is that this median space is isometric to Y. In fact, the isomorphism is given through the evaluation map. There exists. This is omega. So for almost all point inside the omega, when you consider the evaluation map, the projection on this factor, what you obtain an isometry between Y, between this space of section and Y. And note that the G1 action will be by isometry when we undo the space of section by this metric. Yeah, and so here we have defined the action of G1 on Y, and now how we define the deformation of the fiber to say that it is cohomologous to our initial cocycle, to connect it to cocycle. If we can fix a base point, let's say x0, such that the evaluation identify Y with our median subspace, and for each other point, it will give us an isometry on an isometry of Y. So we rearrange this fiber with regard to this isometry, such that what we want to obtain, constant alpha G2 equivariant section. And in this case, the cocycle that we obtained here, when restricted to the second factor G2, it will be the trivial. There is also another way to define the action, and it is by using the reduction of cocycle, where each alpha G2 equivariant section, you deform it to a constant section, and you do it for a countable element of Y, such that it covers the whole point of Y. And after that, what you will obtain, well, you can show that at each step you deform by some element. And you can show that when you compose what you obtain the sequence of the deformation, it will converge to some H. And when you deform the cocycle by this H, you conjugate by this H, you obtain a cocycle which, when restricted to G2, will be trivial. Yeah. Yeah. I think think that's it. Yeah, thank you for your attention. So if